Here we go. Is everybody settled? Turn off your phones, put them away, turn on your heads, and welcome to Control Systems 1. My name is Jacopo Tani. I work in the Institute for Dynamic Systems and Controls, in the chair of Professor Emilio Frezzoli, and I am going to be your lecturer for Control Systems 1. So, what is Control Systems? Why is it important? Why is it amazing from my perspective, of course? These are all things that we're going to discuss throughout the course. I would like to start with two simple videos just to show what control system is all about. Up to now, you have studied, you've attended many lectures in which was very clear what you were doing. Now, you were either studying math or physics or building bridges or figuring out how to do like real practical stuff. Control systems typically is not really, not always appreciated because it's a little bit more subtle. So let's try and see what does control system allow us to do.
And for deep space exploration tomorrow.
So what you can see here is, of course, pretty straightforward. It's a rocket launching. It's pretty amazing on itself. You might ask yourself, well, where's the control systems going on here? I mean, it surely is amazing. Control systems is what it allows it to work, in the sense to operate nominally, to do actually what people want it to do. And while the launch is something you might have seen many times, this video is particularly amazing because look at what they managed to do. They actually managed to land the rocket back, okay? If any of you think that that's easy, have you ever tried taking the stick of a broom and putting it in an equilibrium on your hand, right? If you like close your eyes for 5 seconds, you won't be able to do it anymore. Now imagine if that broom is thrown from the skies and it's like 300 tons in weight. I try now to handle it, and let's see how you do. So control systems is one of the things that allows, for example, these things to do, but it's one of the really properties of this subject that fascinated me when I was a student your age, is how easily it can be, how powerful it is, in the sense that how it can be applied to such a broad variety of topics. There's nothing, I mean, pretty much, I'm sure that 95% of the things you use on a daily basis have plenty of control systems embedded into it, and you probably don't even know. So this is just another application upon the plenty we could mention of control systems. This is a pretty self-explanatory self-driving car. It seems like an easy, I don't know, I guess most of you, who has a driving license in this room? Okay, pretty much everybody, okay? So driving is relatively easy to do if you train and practice. Getting a car to drive on its own without ever crashing, without killing anybody and doing all the nice things that a car shouldn't do is very tricky. In this course, we are not going to go through all the details of how do you actually get a car to drive. That's more robotics, there's lots of other components into it, but definitely we are going to study the foundations of everything upon which this is built. Control systems, in Control Systems 1 in particular, we're going to treat stuff that is maybe a century old, but it's really at the basics of all the stuff you see, all the control systems you see operating in the real world today. So, let's see if we can get this out of the way. So you think that we can apply control systems only to rockets and cars? Well, no. Our control systems, as I mentioned, is pretty much all over the place. It's in the heating systems of your houses. It's in biological systems. It's in networks. It's in aerospace stuff, as we've seen. It's in robots. It's in financial systems. You can apply control systems wherever you want. And the theory that you have to use, it's always the same. And the math complexity of it is roughly high school level math, at least for Control Systems 1. That's one of the beautiful things of control systems. It's easy to treat. It's so powerful in the sense that it's broadly applicable to a bunch of different fields. So it's often referred, in fact, to as the hidden technology, okay? It's something that you never hear about. It's something that is extraordinarily successful. Without control systems, we could not be operating all the things around us in the way we do. How many times have you heard control systems before getting in this room or reading it on my studies? Raise your hand. You know what I mean? Okay. And, but you hear about it a lot when things go bad, when disasters happen. It's often because the control system stopped working, because a sensor stopped doing its business, because there was some weird situation that happened in the computer program that had to make things happen. So what are we going to do today? Of course, we're going to start with the boring things, with logistics, an overview, how this works, how the exams, the people, and all of that. We'll then go, actually no, we'll start from the course objectives, my bad. And then we'll go into the logistics and then start with a little bit of meat of what we're gonna be treating throughout the course. So this course is about controls of what? What does controls mean? It means getting something to do what you want it to do as opposed to what it would naturally want to do. What is this something? The something is dynamical systems. So what are systems, right? So system is a very broad word. In common language, you can use it to say, the system is what doesn't make you get a job, or is what rigs the game of your favorite soccer team, right? No, that's not the kind of system we're going to be dealing with. We're going to be dealing with mathematical, let's say, let's call systems as something that operates transformations between inputs and outputs. So one of the beautiful, in my opinion, things about control systems is that it sees the whole world as blocks, as nice blocks with inputs and outputs. So what is a system? A system is anything that you can think of that represents a transition, a map, a transformation between something that you call an input and something else you call an output. Basically, anything that moves or changes in the universe can be represented as a system. So what is the control problem? So we know pretty much what a system is. We'll, of course, go in plenty of detail about this throughout the course. What does controls mean? Controls means finding what is the right sequence of inputs, because input is something typically that we can do something about, so user can control, can modify. Trying to find what is the right control sequence such that the output of the system, which is what we care about, behaves in a way that is desirable to us. So follows some signal that we call a reference. So how do we achieve control? So what are the steps, the milestones that we'll have to go through in order to be able to do this magic thing of controlling systems in the way we like? We will have to first study about modeling. So modeling is about describing, creating a mathematical representation of a system. That is, things in nature happen all the time. Most often than not, what really happens, it's either beyond our understanding or way more complicated than we care to describe. So models are something that we create, and they're mathematical representations of reality. So the model itself is not reality, it's just everything goes as if it was described by those equations as far as we care. So we'll go into this later in the course, but the general takeaway is that every time you make a model, you're always doing mistakes. All models are wrong, but they're useful. Often they're useful, and they're very useful in control systems. So we'll learn how to do some modeling. Then we'll have to go through the milestone of analysis. What does it mean? So analysis, understanding how systems work. In the sense, if we stimulate a system with some input, whatever the input is, depending on the specific system, how does the output behave? If we design some sort of logic, some sort of black box magic thing that manipulates the input in a certain way, will the output respond in ways that we like to the input? How does it work? How do we quantify the performance and the relationships between inputs and outputs? That we call analysis. And there's a full set of tools that we're going to introduce in order to be able to do this. Finally, we'll have to look at the milestone of synthesis. Synthesis, instead, it's kind of the opposite of analysis. Analysis is, you're given something, tell me how it works. Synthesis is, I want something, you create it such that it works in this way. So synthesis will be the set of tools that allow us to design a controller, for example, so some sort of logic that makes our output behave in the way we want. So we'll get into this later, but the idea is that in this course, we will focus on systems that are described by ordinary differential equations. I'm sure you all know what ODEs are, correct? Yes? Yeah, I would like to see more enthusiastic hands. Like, ODEs are your bread and butter. If you don't like ODEs, man, you might be sitting in the wrong place. Want to consider that when you go home. So we're going to be talking about classical control in the sense that, as I mentioned before, and as it will be much clearer throughout this class in particular, we're going to be restricting the scope of what we study throughout the course to something that is very particular, to a class of systems that, if you want to really be picky, it's like the subset of the subset of the subset of what is really going on in the world. And one can argue, okay, but why is it useful, right? If you're studying, typically, I don't know, every time you talk about something that already has 3 or 4 adjectives in front of it, it means it's so particular, it's so specific, like how can it be relevant, right? But actually, the key element is that this is a subclass of systems that we're going to be describing. They're called linear time invariant systems. They are a good enough approximation of pretty much everything that goes on in the world. So as long as we keep in mind that we are committing a little bit of a mistake in approximating what is going on, even the most complicated of things can effectively be treated through this simple linear time invariant subset of whatever it is. And why is it cool? It's cool because linear time invariant systems are mathematically so easy to treat, and we can really play around with them as much as we want. So some of the important things we'll go through are the determining how to stabilize and find out the performances of the system. These are all keywords that we'll see later on. And how to design, of course, controllers to meet whatever our design objectives are. So one of the things you will notice about this course, and I think personally that is one of the, say, 4 or 5 big secrets of engineering. Like you could summarize all engineering in 4 courses, basically in 4 topics, and this is one of those things you really want to know. It's the Laplace domain, it's Laplace transformations, it's the frequency domain, okay? We will see how useful it is to represent all the dynamic behaviors that we're going to be studying in this thing called the frequency domain that maps one-to-one to the time domain by a transformation that is called the Laplace transformation. And this is kind of counterintuitive. It's not something you can get a feeling of it unless you've got really lots of practice. And this typically represents one of the biggest, let's say, hurdles to students studying control systems for the first time, because quite immediately you lose the physical sense of what's going on. But nonetheless, the frequency domain really is one of the secrets of engineering because it opens the door to what really is going on in dynamical systems, like in the relationship between inputs and outputs. So it's perfect for what we're going to do. But it's going to happen throughout this course that you're going to start thinking, hey, what the hell is it that I'm doing? All these calculations, how are they relevant? How do they matter? How can I do something useful out of it? So not if, panic starts creeping in, keep calm and follow the rules, because it's nice that we can really do step-by-step procedures for most of the important stuff that we're going to be talking about. So let's get into some logistics. So as I said, I'm Jacopo Tani. Dr. Shima Musavi, here you go, is going to be my lead assistant. She is going to be teaching a few of the classes that I unfortunately have to be out of town in a few weeks for 2 different lectures throughout the course. I'll ask you to introduce yourself appropriately later. We're going to have Julian Zilli helping us out for all the academic administrative things, and Ms. Nina Pachter for the more, let's say, department-related administrative things. Lectures are going to happen here, so from 10 to 12 on Fridays in this room. Of course, there is going to be a video transmission in HGF5, so I'd like to thank the guys, I don't know if they see me, I barely see them, that are in the other room listening. You should be able to hear everything we're saying in here. Dario, is that correct? Yes? When anybody of you wants to ask a question, and I will encourage you to ask questions with one little asterisk that I will mention in a few slides, we're going to be using this ball so that they can hear your questions as well. So one nice, okay, we're going to have exercises on Friday, basically just after the class, in various rooms. Go and check the course catalog. If you actually download these slides from the course's site, you will, this is a link, you can just click on it and you'll get there. But we're going to have different rooms. On the course's site, we're going to publish like what TAs are going to be associated to each room. Today, we're going to start with one. I understand that you were maybe expecting this, but we're going to do a non-mandatory, let's say, exercise session where we're going to introduce the basics of Python, which is the programming language we're going to be using to exercise throughout the course. And we're going to do a tutorial today, basically on how to get everything installed on your computer, to how to get you up and running. But it is something that you can just download the instructions and follow step by step and do it at home if that's what you prefer. So one thing that is new this semester is that we're going to have these things called study centers. Every Wednesday, you have these rooms, the opportunity to go there, and you'll find TAs of several different subjects helping you out. So write this down. They'll start from the third week, but the Wednesdays 1 to 3 in ETH E8. And finally, I will be holding office hours, apart from the 2 dates that are written there, in my office, Tuesdays 2 to 3. So another little detail, smile, you're on camera. All these classes are being recorded, and they will be publicly available forever and ever. So not to add it to your stress, but everything you say and do will be just used against you at some point in time. But it's part of how it works, so just lose your fear. That's the biggest suggestion I can give. Hi, Mom, by the way. So here we go to the Control Systems 1 staff. Shima, please introduce yourself. Wait, let's get you. It works. This is meant to be thrown, so be ready. Okay, good.
Hello, everyone. I'm Shima. I've recently received my PhD degree in control. And the reason that I'm interested in this field is control everywhere, and without it, our life is impossible. I would help the TAs of this class, and I may also help in teaching. Thank you.
Thank you. So I will ask now the teaching assistants in alphabetical order to stand up one at a time and to give a brief introduction. You should have the ball there already. So I think Carl goes first. Yeah, Peter. Friedrich goes first. Okay. Friedrich, so you'll say your name and you'll introduce yourself.
Hi, everybody. My name is Friedrich Rockenbauer. I think most of you already know me from further lectures like the Innovation Project or maybe from CAD. I think everybody of you who have seen me before has recognized that I'm really into controls, and this is really what I'm doing. I'm also now in a focus project focusing on that. And I can just say the same as you have heard before. Controls is everywhere, and this is the reason why I'm really into that. Thank you.
Hello, everyone. I'm Giuseppe. I'm a master's student in robotics, and this semester I'm doing my master thesis. I took almost any control system course at ETH, but don't ask me too difficult question, please. And
that's not what we agreed upon.
I should have not said that I took any control system course. Anyway, today I'm gonna introduce you to Python, so I'm gonna be there for the recitation. I hope it's gonna be a gentle introduction, so depending on how tired we are at that time of the day. So nice to work with you.
Thank you.
Hi, I'm Luna. This is my second year as a teaching assistant, and I'm looking forward to seeing some of you guys in my class.
Well, good morning, everyone. My name is Moritz Reinders. I'm here in my third year in Switzerland and at ETH. This will be my second time being a TA, not for control systems. Some of you may have recognized me from CAD last year. I'm also doing a focus project with Fritz, so hopefully implementing many of the things we're talking about here. And I look forward to seeing you all in the exercises.
And Julian.
Hi, I'm Julian. I'll be doing some of the administration of the course, and I'm also really interested in control systems, especially in conjunction with data. This was the modeling part that Jacopo Tani talked about. Yeah, and I'm excited to have you get a glimpse of this subject.
Thank you. As far as textbooks go, basically the lecture slides are going to be enough. We're going to have exercise notes. We're going to put everything on the course site. But we will often refer to as reading, let's say, aid to this very nice Control Systems 1 textbook that is freely available online. So just follow the link and download it. For any of your questions, of course, you can attend the classes of the TAs, which are meant for that specific purpose. But we do have a forum online called the Piazza, which is basically a place where you can post questions, and we are trying to reply within 24 hours to everything. And actually, everybody can see everybody's questions, so we don't get the same stuff answered over and over. And you can actually get answers from your colleagues as well, which is nice. So moving on, this is a tentative schedule of the course. We should be able to follow this pretty strictly, although I maintain the right to improvise sometimes. What we're going to do is we're going to start by talking about modeling, as we mentioned before, and we're going to then move basically in the part of analysis, which is fundamentally all this block here. And then we're going to talk about more the synthesis part. And the idea is that we are going to start by introducing systems. We're going to start explaining a little bit more practically how do you actually get to the mathematical equations describing a system. Again, once we have this, we'll look at this powerful concept of representations. So you have something going on, a physical system. If you kick the ball moves. But in how many different ways can we describe this phenomena of kicking a ball and making the ball move? Well, each different way we use to describe it is a representation. Each representation is good or bad in different circumstances, depending on what you want to do with it. So we'll see there are at least 2 or 3 different representations, mathematical ways of expressing these relationships that are going to be particularly useful to us. And we're going to, thanks to the different representations, we can gain insight about what's going on. And then we'll go a little bit more forward, and we're going to be studying how these systems behave when they are connected to each other, and how can we influence them in an efficient way. How can we leverage the properties they have, or maybe how do we cancel out the bad properties they have, and replace them with something that allows the systems to be controlled, that is, to behave in the way we want them to behave, rather than how they would naturally behave. Towards the end of the course, we'll touch upon some of the more, let's say, advanced topics, the stuff that you will see in future courses in control systems, if you will attend them. Things like robustness and challenges of implementations. So now we're going to move into some of the, let's say, more interesting topics. At the end of today, you should be able to understand what is the approach of the discipline of control systems. That is, this idea of seeing everything as blocks with inputs and outputs, and understanding how to classify systems, what systems are, and how can we describe them at a very broad level, and then we'll pick out of this broad classification what is actually of interest to us, so we understand what's the scope of the course. You should be able to describe what an input, an output, maybe the state. No, we're not going to be talking about states today. Of what system, of some practical examples. You should be able to describe what a control system is to another student and why should they rush and join this course. You will be able to describe some of the more technical properties of systems, which we will see later on, and be able to calculate and at least describe, at least understand the influence of different interconnections of systems. So what happens if we take system A, system B, put them together one after the other in series and parallel, or in this magic configuration that is like the key to solving all the problems of control systems, which is called feedback, like the famous feedback loop. It's all about controls. We're proud trademark to the feedback loop. And then we're gonna you should be able at the end of this class, to describe the difference between a single input, single output system versus a multi-input, multi-output system, CISO versus MIMO. Okay, so let's get started. What is a signal? So are there any questions up to now? Before we get a little bit more into technical stuff. Any questions regarding why is control systems useful? Why in the world should you be sitting here? Apart because it's mandatory for you, of course. Anything related to the organization of the class? Yes, no, maybe? I get it, you're on camera, but really don't be shy. It's not worth it. Nope, okay. Any questions from you guys? No? Okay, so let's get started. Signals. We really are at the point where all we want to get out of this class is imagine the world as a block, okay? And every subset of the world is a different block. Control system likes seeing blocks with arrows that come in, arrows that go out. What comes in is an input signal. What goes out is an output signal. What stands in the middle is a system. What is a signal? Let's start by describing inputs and outputs. So a signal is a function. It's a map. It's a mathematical relationship between two sets of numbers, okay? So basically, a signal is something that you throw a number in and it produces a number as an output. We'll call the numbers that you throw in the signal, let's say the set T, written in that way, and the output is going to be from some other set. Now, depending on how we imagine this set T, which you can, of course, it's called T because you can imagine it as time, although it could be anything else. Let's imagine time goes by, your input signal is something that changes in time. So if we imagine this time axis to be continuous, what you get is a continuous time representation of a signal. And that's the approach we're going to be following for most of the class. Why? Because continuous time is our favorite way to model the world. Things that happen in nature happen in continuous time. But you can imagine this T set to be, instead of the reals, you can imagine it to be like, for example, the natural numbers. So just 0, 1, 2, 3, nothing in the middle. And this leads to a representation that is more discrete. We will call it a discrete time representation. And why in the world should we care about just considering things that step by step, 0, 1, 2, without all the infinity smooth things that happen in the middle in the beautiful continuous world? Well, because that's how computer works. So basically, control systems transitioned from the early days to today, where everything is done on a computer. Like there's these things called microcontrollers, which are basically computers that are the instrument of choice for implementing, to actually bringing this subject in the real world. And everything, and a computer works with zeros and ones. It works with discrete time. It doesn't have a knowledge of continuity. So the discrete time representation is something we'll introduce to understand what really happens when we put our theory inside a computer to make it to do what we want to do. And there are some nuisances. Of course, the big concepts are the same, but there are some nuisances that are not negligible, so we have to address them. So what is a system instead? A system is so wait a sec, I forgot to mention something. No. So a system, what's a system? A system is instead a map between signals. Okay, so we said a signal is something that gets a number in and produces a number out. System, we can imagine it, at least we'll call these input-output models of a system, is something that transforms an input signal into an output signal. Okay, so what are input signals? So the inputs are, again, something that you can think as something you have the control over. You get to choose the input. If you have a ball and you're kicking the ball and the ball goes somewhere, well, you get to choose how much force you apply to the kick, where you want to hit it, what's the curvature you want to give to the ball. It's something you have control over. And the output is just the subject to the laws of physics, what ball you're using, what's the weight, what's the environmental condition, is there wind, is there not, and that's the output is going to be a function of how the system, that is everything that has all the laws of physics that have an effect on the process, how this system operates on your input, and that's the objective of our course, is trying to figure out what are the best inputs so that we get the outputs to be something we like, that we can predetermine. There is going to be other key signals that we're going to mention throughout the course, some things called disturbances, noises, and these are always inputs to the system in a broader sense, but are inputs that we cannot control, are inputs that come from sources that are beyond our reach. For example, let's say that in this room, you are all looking at us. We're looking at these slides, and but if the lights of the room were to go 100% down, then you wouldn't be able to see anything anymore. No? So the environmental lighting affects your ability to sense and understand what's going on. That would be, and let's suppose that I weren't here, so he cannot control the lights, so basically that would be something that we didn't have control over. A noise signal instead is something that is more practical. Basically, every time you use a real sensor to measure something, you never measure really what's going on. There's always some high frequency noise on top of it. And let's say typically the distinction between noises and frequencies that are done is noises are something that is really high frequency. For example, I don't know, if you're using a thermometer to measure something, or like a thermocouple, an electrical sensor of temperature to measure temperatures, there's going to be all the particles that are moving inside of the copper wire that are going to create some high frequency. That's nothing you can do about it. You just have to deal with it, okay? Disturbances instead are typically more low frequency things, but we'll get into the details of all of this later on. So what is an input-output model? This is fundamentally going to be your best friend going on in this course. This is how we see a system. It has an input signal, which we will call U, or an input signal that changes in time, so a U of t, and it will go through the system. The system, for now, we will represent it as this sigma function. And as this system operates, wait a sec. As the system operates on the input, so system is like, it's like a monster that chooses stuff. The input that comes in goes inside gets modified by the system map to produce what we call an output. So this is the signal that is produced by operating by the effect of the system, represented by the sigma transformation on the input signal U. And of course, it's an output. It's a function of time, because as you change the input in time, of course, the output would change as well. So depending on what is the relationship, now we're going to describe a little bit more what systems are. Now, so depending on what is the relationship, the sigma, how it manipulates the inputs to become the outputs, we will broadly classify them in 4 different, let's say, categories that are relevant to us in this course. First, we're going to talk about static versus dynamic systems, static or memoryless systems versus dynamic. We're going to talk about linear and nonlinear distinctions. We're going to talk about causal versus non-causal. Do not mistake, and I will probably do it because it happens all the time, causal with casual. It's like very similar, just a tiny permutation of words, but casual, it's like when you go to the bar. Causal, it's when the future can't affect the past. And then we're going to talk about the difference between time invariance and time variance of a system. Why do we introduce all of this? Well, because what we really care, this is like the preliminary work we're going to be doing to define the scope of the course. What we care about and what we will study are linear time invariant systems. So systems that are linear as opposed to nonlinear, that are time invariant as opposed to time variant, and that are, by the way, causal, not anti-causal. So, and of course our dynamic systems. So let's get started. We have 10 minutes before the break, so we can get started. So let's first get into the distinction between a static and a dynamic system. So what's a dynamic system? Well, you can imagine a dynamic system as something that changes in time. Well, even a static system changes in time. The difference is that in a static system, suppose this is the input signal that changes in time, okay? And we are at the present here, and we just know that at this particular moment in time, let's use a different color, at this particular moment in time, the input signal has this value A, which could be any number, 1, 2, 3, okay? So we send A inside the system reacts to this number and produces an output at that specific time instant that is called B here, okay? And this is happening at a specific time instant in the present. Let's suppose it's time t is now, okay? In a static system, basically, if we change the input signal, so before we had something that was more like this, let's say, if we change the input signal, but at the present it still has that particular value, then the output will change, but at the present the value is going to be the same. So another way of saying it is that in a static system, only the present input value affects the output. There is no effect of the past. That's why it's called memoryless, because the system doesn't have to remember anything that's been going on in the past of the input. The output of the system only depends on the present value of the input. So basically, you can forget anything that goes on anywhere apart from now in a static system. Any questions about this? So there are some examples. Might be boring for some of you, but let's just start slow. So let's go through maybe 1 or 2 of these things. So what did we say is a static system? A static system, the output depends only on the present values of the input. It's like, be careful. So let's look at this thing. Y of t is equal to 3 u of t. Well, let's pretend we get t equal to 0. You've got y of 0 that is equal to 3u of 0, right? Well, if this is the present, the output at the present time is 0 is affected only by the input at the present time 0. If we were to get a different value, t equal 5, we will get y of 5 is equal to 3u of 5. Well, it's not really a rigorous way of doing it, but you can tell that whatever time instant I will choose, the present output will only depend on the present input, right? Does anybody of you disagree with this? Yes, no, maybe? No. Let's look at the next example. This is a little bit more tricky because when you think about static stuff, you would say, hey, as long as I only see u of t on the other side and t doesn't appear anywhere else, then it's static, right? No, not really. So for example, here if I get t equal to 0, you've got y of 0, that's equal to 2 at it's 0 plus 1, 1 u of 0, right? So, well, if I use maybe another value, y of 3, this becomes 2 at the minus 4, u of 3. So you see, there is time here in this system, in this relationship between these input and output signals, time that appears outside of the input. But it's a coefficient, okay? So a time-varying coefficient doesn't really affect the dynamic or static nature of a system because the output at the present time instant only depends on the input at the present time instant. Doesn't mean that there's something else that varies in time in a different way, like a coefficient. You can crank through the other 2 examples here on your own. But for example, look at this. Look at the integral. Is the integral a static or a dynamic system? Well, what is an integral? An integral is an operation that does what? Does sums, right? It sums up stuff. Sums up stuff from the beginning, from one of the ends to the other. So in the way we wrote the extremes of the integral, we're summing from minus infinity, from the Adam and Eve, from the beginning of time to now, time t. So in this case, we are basically, the output is definitely a function of past inputs as well, because you have to sum up u at minus infinity plus u at minus something, infinity plus something, all the infinite values that come from a minus infinity to now. And that definitely doesn't make it a static system, because if it were static, y of t would depend exclusively of u at t now. What about the derivative? operator. If you have y of t is equal to u dot of t, is that static or not? What's a derivative, right? So if you can imagine this is time, you have whatever signal here. If you are doing a derivative, what you're really doing is you are calculating a slope at some specific point, right? So a slope is a line. A line, we know since we're in elementary schools, that needs at least 2 points to be well determined, right? So whether you choose the point to be at the present and one in the past or one in the future, and we will talk about this later, but there's different ways of calculating derivatives. The bottom line is it doesn't depend only on what's going on in the present. You must have some sort of other piece of information, otherwise you cannot well define a slope. So definitely a differential operator is not static, it's a dynamic operation. You can imagine, for example, now this is another interesting maybe example, which is this. So y of t is equal u of t square. So what does it mean? It means you take time and then you apply some kind of operation on time. There is some sort of time scaling going on, some sort of time manipulation. Well, if you do y of 0, you would say, this depends on u of 0. So present and present, perfect, it's static. If you do u of 1, you say, this is u of 1 square, which is always u of 1, right? So static, it's, oops, this is a y, sorry. So it's always present output, present input, boom, done, like no problem. But actually, if you now get another number, for example, 2 or some negative number, but you get the gist of it, this will no longer depend only on the present value of the input. So if you do any sort of time scaling, you will not get a static system. Another nice example is a system that is defined in this way. So when you take the input at some current time, we'll talk about this later, and you shift it. Well, that's in this case, suppose A is bigger than 0, what you're saying is, I am taking an input now. It's like if I hit this table with my pen, and somebody at the back of the room will hear the noise of it after some time, because sound needs to travel to get there, right? So the input is when this hits here, the output is when somebody at the end hears the sound where there's a delay. Whatever happened here, the output comes after a while. So this transition, with this translation in time, if A is a negative number, represents a delay. Delays are a very common thing in control systems. We'll see them all over the place, so start getting used to it. If A instead is a negative number, then it means there's some sort of anticipation going on. It means the present is affected by the future. That's a very weird concept, and we'll describe it later on. Are there any other questions on static and dynamic systems? Yes, no, maybe? You can ask questions. I actually appreciate questions. No? Doesn't work? Okay. I guess we can go and pause now. There's only 2 minutes until the break. I'll see you again in 10 minutes, 15 minutes. How does it work? 15 minutes. See you later. Please settle. Time is ticking. You're losing opportunities to learn about control systems. How will they ever come back again? Okay, so ready or not, here we come. We've just been finished looking at the difference between static and dynamic systems. And really, the core idea is that a static system depends, has an input-output relationship that depends only on the present. That is, the output at the present, now, at time step t. Guys, please focus, sit. Thank you. Depends only and exclusively on the input at the present time t. Anything else is dynamic, okay? So now we can talk about the distinction between causal and non-causal systems. And it is very important. And it's very much related to static and dynamic. So what is a causal system? A causal system is a system that makes sense. This is not a technical definition, okay? Makes sense, what does it mean? It means that it follows the principle of cause and effect. Like the effect follows the cause. If I kick the ball moves. The ball doesn't start moving before I kick it, okay? So the way we can say it is that a causal system is a system where only the past and the present affect the past and the present of the input affect the present output, but not the future. Okay, so a causal system is a system where the future does not affect the present. It's fair enough, right? As you see, you've got a signal. There is all the past of the input up to this current time t has an effect on the output. But the future, we could change it. We could put it to 0 if we want it. And the output signal up to here would be exactly the same. Now, why is it important? This concept of causality is important because all systems that are practically, physically realizable in the world are causal systems. There's no way in the world you're going to be able to create a piece of metal, a circuit, a piece of machinery, I'll call it whatever you want, a program, something in the real world that operates based on an anti-causal or non-causal principle, okay? This is important because moving forward, we will see that sometimes we get fancy mathematical solutions to problems that would work and would allow us to do whatever we wanted. But these relationships actually would indicate that in order to make things work in the real world, we would have to have the future affecting the past, and that's not something we can do for now. So let's keep this thing in mind, that all realizable, practically, physically buildable systems are causal systems. In a more mathematical way, how can we represent this? We introduce an operator. It's like a transformation, a truncation operator. That what it does, it truncates. Basically, it sends to 0 everything after a certain time instant. We choose the time instant to be the present, time t, or some time. And as you operate the truncation operator on an input signal, what you're doing is you're setting the input signal after that specific time to 0. Boom. Okay. Why is this useful? Well, because causality is about the future not being able to affect the present. So basically, if we translate this in a more mathematical way, what we're saying is that if you take a signal, an input, and you pass it through the system, you get the output, and then you take away from the output everything that belongs to the future. That's exactly the same result as if you were to take the input, before passing it to the system, you remove anything that has to do with the future, then you pass it through the system, you get the same output as before. When this relationship applies, a system is causal. So basically, it's the same thing if you remove all information regarding the future from the input before or after it passes through the system. So, but the fundamental, this is not going to be very useful in practice. The fundamental idea of causality is that the future does not affect the present. And we call a system strictly causal if only the past affects the present. So not only the future, but not even the present affects the present input. And this is something that in practice is quite common. So let's do some examples. Remember that all realizable systems, all stuff you can actually build, are causal systems. So of course, y equals to u is a causal system. If that's trivial. Plug in any time instant. The output only depends on the present. So it's causal. It's not strictly causal. Now let's look at the second example. We talked about this before. Let's say you've got the input, but it's translated in time. Okay. So what does u minus tau mean? This is a system with a delay if tau is bigger than 0. So let's talk about it a second. Suppose we have the time axis here, and you've got a signal that is 0 up to here, and then it goes whatever. This is u of t. Okay. And you've got, let's say tau is equal to 1. I don't know, just to put in a number. And what does it mean? It means that y at time 0, for example, is equal to what? Is equal to u at time 0 minus 1, which is u at minus 1. So the output at this instant in time is actually equal to u minus 1, which is here. So it's as if you're taking the input signal and you're translating it and you're looking at what happened in the past. So when you subtract, you translate the time axis by a positive number, what you're doing is you're actually implementing a delay. And delays are really, really common in all world applications. Say you are asking even a very mathematical trained person like Julian, you say, Julian, how much is 3 plus 2? He'll take a split second, but it will take some time to actually calculate that before he tells us the solution, right? So there's an input, my question, there's an output, his answer, but even if you have an extraordinarily mathematical person, it will take some time. Even a computer will take some time. So that time is a delay. There is pretty much always a delay between an input and an output in real systems. Imagine you're fishing. You're holding your fishing rod from the bottom. You apply a torque to the fishing rod, well, the tip of the fishing rod moves after a while, right? Because there's this mechanism of flexibility of the rod. That's a delay in a different sense, but it's always a delay. Let's look instead, so this is definitely a causal system, right? Because if we are to, actually this, if tau is bigger than 0, it's a strictly causal system. If you plug in any number of t, you will never have y at the present being affected by the number in the future, right? But t equals to, I don't know, 3, you get y of 3 is equal to u of 3 minus tau. Tau is bigger than 0, so u as 3 minus tau is always less than 3, right? Now let's look at it in another perspective. One could say, I got it. So causality, as long as you don't have t plus something, it's good. That's how you lose points on exams, right? So again, the key is always remembering that these definitions have to do, at least the ones we talked about up to now, have to do with the relationship between the input and the output, the signal u and the signal y, not with anything else, okay? So in this particular case, we have a coefficient here. So it's a number that multiplies the u, okay? And that is time dependent. If I plug in here t equals, I don't know, 0, what you get is y of 0, it's equal to the cosine of what? Of 1 times u of minus 1, okay? Well, the present input is affected only by the past output. U at time minus 1. If we call 0 the present, minus 1 is before the present, so it's the past. Now that we had an operation here of adding something to time, well, sure, that is a coefficient. It's a number we're multiplying to our input. But the output only and exclusively in this example depends on the input at a previous time instant. There's no future input involved, okay? So it's a causal system. Is this clear? Do you have any doubts, questions, or comments? I see weird faces, so. Julian, is this clear? It is. Okay. Julian says so. You can blame him at the end. Okay, so let's look at something else. Let's say, is an integral something that is causal? Well, depends. You have to be careful here and not generalize. For example, this integral here is definitely causal, okay? Because an integral, remember, is a sum, right? So what you're doing is you're saying this is t. We've got this weird signal here that is u of t. Let's step back a second. Is every one of you in this room really comfortable with the mathematical notations? Do you understand what an integral between minus infinity and t of u of tau and d tau is? Do you know why I used tau inside and not a t? How many of you understand why I used a tau and not a t? Okay, so some didn't. So the point is, whatever you put inside the integral doesn't really matter. It's a silent variable, okay? So I could have used a flower, a house, or a ball, or better not to use t because it's confusing, okay? Why is it confusing? Because I use the t up here as well, so it's kind of really the only choice you don't want to make. But so when is it that, so what we were talking about these integrals. So what is an integral doing? Let's suppose this is time t, okay? Well, what an integral is doing is summing up everything that happened from the beginning of time till time t, okay? So basically it's taking u at t minus infinity plus u at t minus infinity plus epsilon, where epsilon is a small number, positive small number, as small as you can imagine it, and doing this continuous infinite operation until now. It's a causal system, very well. But suppose instead, and I'm looking at this example down here, that instead of t, you had the extreme that is t plus 1, okay? Well, in this case, the system is not causal anymore, because the sum would arrive up to t plus 1. And if t is your current time, because the output is at time t, then summing up to t plus 1, it means you are considering the future. The future was affecting the present. That's not causal. So don't just remember integrals are causal. No, integrals depends on the integrands and the extremes of integration. So for example, if I had another example, like y of t is equal the integral from minus infinity to t of u of tau plus 1 in d tau, this would be non-causal as well. Because the trick is just take the last the integrand, put it inside, you get u of t plus 1. So it means you did all the sum up to what's the most recent value. It's something that comes after t. If t is now, t plus 1 is a little bit more than now. So it's the future. So this would be non-causal either as well. So other example of non-causal systems. Well, definitely a system that is anticipatory. So don't make yourself be fooled by the fact it's t minus a. A is a number, right? What is a number? A number could be anything. We have to define it. So in this case, it's a real number, and it's negative in this case, though. So if you're doing minus a negative number, really you're adding something, right? So this is a system here. All it's doing is saying you're doing y of t is equal to the input at the present time plus something. The system is actually not only non-causal, but it's anti-causal. It's exactly the opposite of a causal system. That is, it's only affected by the future, not even by the present or the past. Not really relevant, just for your information. Other cases, well, I guess this is obvious. This time scaling is a little bit the same concept as before. If I put y of 0, you get u of 0. If I put y of 3, you get u of b times 3. And if b is a number that is bigger than 0, then we're warping the time axis. We're doing a time dilation. So effectively what's going on is that the future is affecting the present in this case. So it's a non-causal system. Now, this is an interesting question. Typically, it's like, I encourage you to think about it. Is the differential operator a causal or non-causal operation? Is y of t equals u dot of t a causal system or not? And is it realizable or not? So I will not crank this through. I'll just give you the answer and tell you to think about it. Just prove it at home and see if it really you are convinced about it. The idea is that it's a causal system, but it's not realizable. So every realizable system is causal, but vice versa is not necessarily true. Any questions, comments, or doubts? Yes?
What do you mean with non-realizable?
It means you cannot create a machine that can actually do a derivative, not physically implementable in the real world. And the idea, fundamental idea behind this, say the intuitive reasoning behind the derivative not being realizable is that, so a derivative, what is a derivative? Now the integral is the area under a curve, the derivative is a slope, right? So if you have a signal that emits a derivative, let's suppose it's continuous, C0, so it's continuous, but the derivative itself can have arbitrarily big numbers. It could be a very, very high slope. And in the real world, so when you talk about realizable stuff like physically implementable systems, there is no such thing as infinite energy in the universe. Not even the sun has infinite energy, okay? So you will never be able to create a piece of machinery that is able to measure an infinite gain, for example, an infinite slope. Imagine you're getting a measurement from some instrument, okay? And you have some noise on top of it. White noise is something that is characterized by having random, basically, variations within some bound, but at all possible, this is an idea, it's going to be much easier to understand later on when we know about Laplace domain, but it has energy across the whole frequency spectrum. This means that there's arbitrarily high variations of the noise, okay? So if you were to measure the derivative of a noise, this is like one of the biggest takeaway of the whole course. At the end of the course, was one thing you want to remember, and never take derivatives of noisy signals, okay? But the idea is that this derivative could be infinite. So there are ways to, of course, approximate derivatives. but you cannot actually calculate the derivative. You can do very close approximations, but you cannot calculate it exactly. And now we get to this other idea, which is the idea of time variance versus time invariance of a system. So what does this mean? So you can read, of course, the definition there. I'm trying to come up with an example that is intuitive. Suppose that it's like really not a good example, but suppose that I go and operate that door. I want to open it and close it, right? If I give to the door an input, like I push it, it's gonna swing in some way. Now, if I wait 5 minutes and I go and push it again, it's gonna swing in the same way. If yesterday I came here and I pushed the door, it would have swung in the same way. How many? Maybe in 100 years it's not gonna be the same because the screws are gonna, whatever, it's gonna, the springs are gonna die off. But suppose it's an ideal door, okay, that the components are never gonna break down. That would be a time invariant system. So a system is time invariant when the relationship between the input and the output does not depend on the time of the day you use it. It doesn't depend explicitly on time, okay? So more formally, we can consider the shift operator. We described it before. Basically take a signal and just translate it in time by a factor tau. Tau is bigger than 0, we called it a delay. If tau is smaller than 0, you're actually anticipating the signal. But just let's consider this shift operator. It's basically something that if you apply to a signal u, if we define the shift operator sigma tau, so you're shifting of a quantity defined as tau, then all you get is the signal at this time instance minus tau, where tau is any number you want. So when is a system time invariant? A system is time invariant when the relationship above holds. What does this mean? It means the fundamental intuitive idea is if I send an input to a signal, the output you get doesn't matter if that input was sent yesterday or tomorrow. The output is always the same. It's invariant with respect to the time of the day that I'm using it. Doesn't mean it's not a function of time. Of course, the output is a function of time because the input changes in time. But there is no direct relationship between time and the output. So this can be shown in this way. Take your input signal and shift it in time. You get this, okay, you get your input signal, you shift it in time of a quantity tau. Here we're supposing tau is bigger than 0. And you get this signal that is sigma tau. It's the shifted version of tau. This is basically u of t minus tau. Now you take this shifted signal and you crank it through your system. Remember, we're talking about properties of systems here, okay? So we're talking about sigma. So sigma in this case, so the output is in this case the sigma, which is the system operating. It's better maybe to write it like this, operating on the shifted input. And it produces as an output, for example, something like this. Now imagine to invert the two operations. So you have the input, non-shifted, and you pass it through your system. After passing it through your system, you get an output that is defined by whatever the relationship is. And we'll see some examples later. Now apply the shift to the output. So you're shifting the output after the input passed to the system rather than doing vice versa. Well, you get a different signal, which is the shift operator applied to whatever the output of your system was. Now, let's call this new signal y tilde. And let's call this signal y of t minus tau. If y tilde is equal to y of t minus tau, your system is time invariant. Time invariant. If this is not equal to t minus tau, it means that if I operated the system before or after, the output would have been different. This is time variant. Let's look at some examples. So, for example, let's take this system here. Here there are some nice properties that we can extract so that when somebody might or might not ask you these questions in a final exam, you kind of don't need to do the calculations. You extrapolate. Once you understand the properties, you can crank things through a little bit more quickly. Okay, so let's apply the trick. So what's the trick? Let's repeat it here for a second. Let's say we have an input signal, okay? And it passes through a shift operator of tau delay. And you get u of t minus tau. Then you pass it through your system, and you get y of t minus tau. Now suppose you take the same input and you pass it instead through the system first. So what we're doing is we're flipping these two systems. And what you get is you get the system applied to you. And then you shift it, okay, of the same quantity tau. So what you get is sigma tau applied to this. Now, if this is equal to y of t minus tau, we've got time invariance. If not, it's different. We got time, so this is different from t minus tau. We got time variance. So let's calculate these two cases here. So let's call this path 1, let's call this path 2. Let's do step 1 first. So you got an input, u of t, you pass it to the time shift. So what's the time shift operator? The time shift operator is something that if it's applied to u of t, it produces u of t minus tau, right? This is the definition of time shift. It's what we said before. If you apply the time shift to u, what you get is whatever u of t, whatever was in the argument of u, that is t, u minus tau. You add a term to it. So in this case, what we're sending in is u of at, right? So let's pretend that at, because it's a little bit confusing, let's call this something else. Let's call it, I don't know, k. Okay? So what we're doing is we're taking u of k and we're sending it through the shift operator, right? So this is exactly as the definition before. What we get is u of k minus tau, right? Anybody disagrees with this? Am I doing mistakes? Oh, good, right? Okay, now we get this u of k minus tau. And this is actually what? This is actually at minus tau, right? Because that's how we, k was equal to 80. Now we take this and we pass it through the system, right? So if we're passing it through the system, what are we doing? The system, we're getting an output that what's doing, it's taking the input and it's multiplying by a the time. So let's call this, just to make it easier and similar to the definition of the system we have here, we can call this, I don't know, n. So the output is going to be what? The output is going to be y of a times n, which is equal to a squared t minus a tau. Now, let's instead do the opposite thing. When we do the opposite thing, we take u of t, we pass it through the system, and we get, so we got u of t, we pass it through the system, what we get is y. How is y defined in this case? It's defined as the system is, what is the nature of the system? Here the system is taking u at some time and it's multiplying it by a. It's multiplying it's dilating time by a. So you get u of t, and here you get u of at. Then and this would be the system applied to the input. Now, what we're doing is we have to apply the time shift. So what's the time shift? Well, we have u of at. Let's call this whatever, k as we called it before. So what you get as an output is u of k minus tau, which is u of at minus tau. Now, this is different from this, right? It's not the same thing. If you invert the time or the delay or the system, you get to different results. So this system is time variant. If you operate it yesterday, tomorrow, or you get different results. You can crank through these examples by just trying this exercise. First, apply the delay to the input, and then calculate the output. And that's step 1. You get some output. Then, next step, invert the system operations. Apply the system transformation to the input, and then whatever you get at the end, you delay it in time. Check if they're the same. If they're the same, you're good. The system is time invariant. If not, it's time variant. Is there any question on this? Yes?
Is there an easy example for such a time variant system?
An easy example for a time variant system. Yes. Do you have a time variant system? It's like anything that is...
If you drive in the summer or if you drive in the winter, that makes a difference. So the car might change, you might have different wheels, so it varies with time. It doesn't behave the same in
anything that is affected by seasons, anything that is affected by day and night cycle, anything that is affected by consumption of components after repeated use, anything that of which the describing properties change in time. So it's not about, the time dependency is not just related to I change my input in time, but it's related to the point in time itself. So if you apply a constant input instead of obtaining a constant output, if you were applying this constant input yesterday, you would get a different result than if you were applying it now or tomorrow. Finally, we get to the maybe most important property, which is that of linearity. We talk about linear and nonlinear systems. So what is linearity? Linearity is I mean, mathematically we can say a system is linear when it's when you can apply the principle of superposition. That is, if you send the sum of two inputs, you get the output that is actually the sum of the two outputs independently. But we can break this down in two properties. One is additivity. So suppose you send a signal U1 through the signal, to the system, you get an output. We call it YA. Suppose you send a different input, UB, you get a different output, YB. Okay. Now, suppose you send in UA plus UB to your system. Well, if the output is just YA plus YB, which is, if you send the sum of the inputs, you get the sum of the outputs, is, you would call that an additive system. If you scale the input, you get a scaled output. That's called homogeneity. And the two things very much related, of course, to additivity. But if you put everything together, you say, okay, if I take two inputs, and I call the output to each independent input YA and YB, and just scale them of arbitrary quantities, well, if you pass them to the system and you get alpha YA plus alpha YB, what you have is a linear system. So key idea, key takeaway of linearity is you can apply the principle of superposition of signals. If you send in the sum of inputs, you get out the sum of the outputs. There's no weird phenomena playing some other role. So how can we see this? Well, the way we see it is by checking these two properties, basically, the property of additivity and the property of homogeneity. So let's see. Let's see. Choose one. Okay. This I think is the most. This one is interesting. So it seems very easy, right? We've got the y is equal to u plus a number. Okay, where a is any number. It's I don't know, a positive number. A may be bigger than 0, real. So let's see what happens if let's check the two properties at the same time. First, we check additivity. Now, what does it mean? Remember, if additivity means I send in a signal, let's call it U1, through the system, I get Y1. Then, independently, I send U2 through the same system, and I get Y2, okay? Then, it's additive if I send in U1 plus U2, you get, as an output, Y1 plus Y2, okay? And the other property is instead that if you send U1, you get Y1. If instead you send U1 multiplied by some number, what you get is the output multiplied by that same number, okay? So let's see, for example, here. If I take U1, the output is going to be Y1, which is equal to U1 plus A, right? If you take U2 as an input, the output is going to be Y2, that is U2 plus A. Now, if we send in the sum of the inputs, which is U1 plus U2, you get as an output what? You get U1 plus U2 plus 2A, right? Now, if instead you were to, if you send the sum of the inputs, you get an output that is the sum of the outputs. If instead you were to, mistake. If you sum these two outputs, you get Y1 plus Y2 is equal to Y1 plus Y2 plus 2A. Okay, that's the sum of the outputs. Now, what happens if I send it to this inside the signal, an input that is the sum of the two inputs? So let's call this Y1. So the way to get this to work from the mathematics, just call y1 plus y2 as a different input. Let's call it v, okay? And now we are in the same case as before. So if I send the signal v inside here, what you get is y of t is equal to v of t plus a, right? So what the system is doing is taking the input and it's adding a, right? If the input is, in this case, the sum of u1 plus u2, you see that the output when you send an input, that is the sum of two signals, is y1 plus u2 plus a. But if you sum up the outputs of the independent things, you would get y1 plus y2 plus a, so plus 2a. These things are different. The system is nonlinear. It doesn't respect the superposition. Is this clear? Comments, questions, or doubts? Speak up. No. Let's see examples, an example instead of something that is similar, but linear. For example, this one here. So what we do, first we check if we have input 1 goes through the system, generates output 1, which is a u1. Then if we do it with the second signal, we get u2 is equal a u2. Okay? Now let's sum them up. If you sum them up, you get y1 plus y2, that is equal to a1 plus u2. Now let's calculate independently what happens if I were to send as an input the sum of u1 plus u2. So what we do is we call u1 plus u2, we call it, for example, v, just to make it easier to match the notation we had before. Now what happens if I send the v inside this system, that what it's doing, it's multiplying the input by a number. It's indicated like this. So this v is what ends up popping inside the input place of the relationship. Your output is going to be a times v of t, where v is equal to u1 plus u2, right? So in this case, they're the same, okay? And if you try even the other property that you scale, you'll get the same number. So this is a linear system. If you should try all these other examples at home, so you get some practice with these things. But here you have a list of linear and nonlinear. So we're done with all the mathematical properties that are of interest to us in describing systems. So why did we do all of this? We did all of this because in this course, really what we're going to talk about is linear time invariant systems that are single input, single output, and are causal, okay? So all of this was done in order to give you an idea of the scope of the course. That is, what we're going to be treating, how does it fit in the bigger picture? It fits in the sense that, really, we're doing a detail of a detail of a detail of the detail. Actually, most of the systems that are in the real world are nonlinear, for example. Okay, it's like, well, we're going to be studying linear systems. So why is this, why are we even doing it? Why is it worth our time, right? It's worth our time because, as we will see in next class, linear systems can always be used as approximation, local approximations of nonlinear systems. So depending on, linear is a very specific thing. We just described what it is. Linear is a system that respects a specific property that we can write down, okay? Nonlinear is everything that does not respect that property. So like linear is something you can put a nice circle around it and define it. Nonlinear is the rest of the world. So the point I'm trying to make is that there is a broad variety of different nonlinearities. When you say linear, you say something specific. When you say nonlinear, it doesn't really mean anything. You have to specify what is nonlinear. So depending on what kind of nonlinearities we're dealing with, the linear approximation can be more or less, let's say, accurate. But as long as we keep in mind this fact that we're committing errors, we can rely on all the instruments, all the tools we will be building upon on this study of linear time invariant systems to treat things in the real world. And in fact, indeed, really most of the control systems you find out there operating in your cars, in your computers, in your ovens at home, in the shower, whatever it is, they're based on linear time invariant systems analysis, okay? So what we're gonna do in this course really will give you the tools once you're out of here to get things to work that before it didn't work, basically. Okay, so we described a little bit what a system is, right? And we said systems can be these many things. And by the way, I think this is kind of obvious, but let's just say it. SISO means a single input, single output. We kind of assumed it. We have our system. Something wrong about that? Yeah, no? I'm missing a piece. So you send an input inside, you get an output, okay? In theory, you could do a system that receives as many inputs as you want and produces as many outputs as you want. For example, if I am taking a chair with wheels and I'm moving it around, well, if I'm pushing with one hand, one finger, and all I care is like the position of the center of mass of the chair, it's a single input, single output system, right? Well, depends how you represent. But let's suppose now I'm using two hands and I'm moving this like it's a cart at the supermarket. Well, now I have an input which could be how much I push with the right hand. The other input is how much I push with the left hand. The outputs could be what's its position X, Y, how high it is, how it's rotating. So it really depends on how you model a system, but it's actually more common to have systems with multiple inputs and multiple outputs, which are called MIMO systems. Guess why? And, but we all restrict our analysis to CISO systems. MIMO systems is something you'll study in control systems too. And fundamentally, all the ideas that apply to CISO systems kind of apply in MIMO systems as well, with some extra complications and spices on the top. But I'll leave that to the next semesters. So now we understood what we mean by system a little bit more. We still didn't specify, like, and saw exactly what kind of systems, how this thing is practically useful. But we reduced the scope. We removed infinite systems that we don't care about. Now we're going to care about the linear time invariant systems. And what happens if you take a system and you hook it up with another system? You do interconnections of systems. What does it mean? Suppose I send an input to a system. So first a system, sigma 1. And you get as an output, I don't know, we can call it y1, which is equal to sigma 1 times u, right? Now, the serial interconnection is when you have the output of this first system that goes into the output of, the output of the first system is the input to the second system. So the final output, y, is what? Is a sigma 2, so let's pretend. So this is the output of the first system is equal to sigma 1 times u, right? And since this is at the same time the input to the second system, let's say that this, we call it u2. So y is equal to sigma 2 times u2, right? This is like what we've been seeing up to now. But u2 is equal to sigma 1 operating on u. So this composition of two operations, now it seems a little bit too theoretical, abstract. Later on, it's going to become a little bit more clear. But the idea is that you can substitute, how do I do this? Whatever, you can substitute this whole serial connection of systems with a single system that you call sigma, that is equal, that has the map that is the sigma 2 times the sigma 1, sorry, as indicated here. In this case, you can represent a serial interconnection of systems as a single block that has the two operations of the system, of the independent systems, hooked up in a certain way, and they're equivalent. Now, what happens if you have a parallel interconnection? So you take an input, you send it through a system. Take the same input, you send it through a different system. And you take the two outputs, you put them together. What is the final output? What box should I have to put in here so that if I represent this as a single input-output, I get the same result as a parallel operation? It's relatively straightforward to see that if you send the input here, the output is going to be sigma u1. If you send the input to this other system, the output is going to be sigma 2u. This circle here is what we typically use in control systems to indicate sums. When you don't specify it, it's just a sum over every different arrow that comes in. Sometimes, like for example, in this case, one of the two directions is specified. There is a minus, so you'll subtract the signal that comes in that way. But basically, y here is equal to sigma 1u plus sigma 2u. So when you have a parallel interconnection of systems, you can substitute the whole thing with one block that is basically the sum of the two systems. So this, if you do the sum of sigma 1 and sigma 2, and you operate on one input, you get the equivalent answer. And these are the relatively simple ones. Now, at some point, somebody came up with this feedback connection, which is beautiful because it basically will save our life infinite times from now on. This will become your favorite thing, so please listen carefully. So, so what is a feedback? A feedback is when you're sending an input to a system. You're taking the output, and then you're taking that output and bringing it back to the input of the system again, summing it up to the input that was before. So you're creating a loop. And one would say, why in the world do you want to do that? Like, whoever came up with this thing, you wake up in the morning and you start feedbacking stuff, like, no. But it's like pretty obvious. It's something we do every day without even realizing. We operate in a world like I want to walk from here to there, so I send inputs to my legs that I'm walking down the road. But at the same time, I am looking at what's going on, right? If some of you push this chair in front of my path, well, I'm not just going to continue walking straight. I will have my output at this point is going to be, I see what's going on. I have to reach the garbage bin, but I want to make sure I have a free path. Now I see an obstacle, so I am feeding back the information I get as output to the system, and as a consequence of that, I'm gonna change my strategy, my input. I'm gonna move my right leg more than the left one so that I can walk around it. The feedback loop really represents, now we're talking about it mathematically, we'll get into the physical stuff later on, the physical interpretations, but it really represents the very common actions of doing something, perceiving what is the result of our action, and then taking a decision based on that result. So it's kind of you think about doing something, well, then you do it, then you perceive what's around you. As a consequence of what you see, you'll then take a different action, right? This circle, this cycle, it's what is represented mathematically here with a loop. And in particular, we're looking at a negative feedback loop. Why is it called negative? Because there's a minus on the feedback branch. So this here is called the direct branch. The feedback branch is what comes back. And let's look at why the transfer function can be represented in that way. So one way of doing it is always starting from the end. We can say, look, what is y, right? Here, how can we represent the signal y? Well, the signal y here is, let's say, 5 minutes early. I have to learn the 5 minutes break. Okay, we can start from this from next class. Nearly finished.